So yeah, and those old rocks on Earth have been really just tortured by geologic processes. So they really don't, they are old, but they don't any longer represent what they started out as, okay? So these asteroids really achieve that for us, this look into the past. So the key science objectives of our mission over a decade-long period were primarily to return and analyze a sample of a pristine, carbonaceous, early solar system sample from the surface of Bennu. And I'll talk about carbonaceous and what that means in a minute. We had a spacecraft system requirement to return about 60 grams of material. That's about 2 ounces, 0.13 pounds, 30 sugar packets, and if you like liquid ounce measures, that's about a jigger. We also have contact pads, and you'll see those in some photos later, but they are on the end of that arm, they are the things that are meant to touch the uppermost surface and collect what we call the space-weathered part of the surface. So because the asteroid doesn't have any kind of atmosphere, it's constantly being bombarded by particles and the solar wind and all kinds of stuff. And we try to understand those processes because it changes the chemistry of the stuff on the very surface. So we have those contact pads to collect that in addition to whatever we get from the disruption that we do during the sampling that you'll see in a little bit. The spacecraft had all those scientific instruments on it because we wanted to map the geology and the composition of the asteroid to provide context for the sample. I'm a geologist by training, and you can hand me a rock and I can tell you what kind of rock it is, and I can tell you something about how it formed based on what kind of rock it is. But if I don't know where it came from, that's about all I can tell you. I don't understand the significance of that rock if I can't put it into a broader context. If you tell me you picked it up on the side of Mount St. Helens, now I've got some more information. If you tell me something about the composition of the lava flow that it came from on Mount St. Helens, now I have more information. So we want that context of the asteroid to help us interpret the sample. We had a goal of trying to understand the factors that affect asteroids over time and make them potentially hazardous or not. I won't be talking about that at all tonight, and I also won't be talking about how we compared observations of the asteroid to ground-based observations from, for example, telescopes, ground-based telescopes. The OSIRIS-REx mission launched in 2016. We proposed the mission to NASA in 2010, and we were selected for flight in 2011. It took us that long to get everything built, launched. We took 2 years to get there. Then we spent basically 2 years operating around the asteroid, including the sample collection. Then we departed and came back to the Earth over a 2-year period. And then the sample arrived in September of 2023. And we are out here, and the mission ends over here. All right, so what are carbonaceous materials? If this is a term you haven't heard before, you can probably deduce from the carbon part that there's carbon in them. But that in and of itself isn't particularly useful information. Something to know is that meteorites are not all the same. They are classified in different categories, and this is a tree describing that classification. The most important thing to recognize is there's this branch here called undifferentiated, and then this branch down here on the right called differentiated. The main difference between these is whether the parent body that produced those meteorites has undergone significant geologic activity or not. Undifferentiated means pretty much almost nothing has happened to that thing since it formed. If it's differentiated, what that means is that usually there was some sort of large-scale melting, for example, that went on, volcanism, bigger geologic processes, okay? The Moon and Mars produce meteorites that we have collected here on Earth, and so the Moon and Mars fall into this differentiated category because they're very large bodies that have active geologic processes, or at least did in the case of the Moon. So the undifferentiated ones are called chondrites, and I'll talk about what that word means. but we're over here looking at the ones in the carbonaceous class. And then within the carbonaceous ones, there's a whole bunch of minor subdivisions. There's a humorous kind of joke among meteoriticists about whether you're a lumper or a splitter, because some people like to divide these things very, very finely. It's like, oh, this one thing is different. That's a whole new kind of meteorite. And then there are other people who are like, no, 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 these are all the same thing. So there's this, you know, classification that has been developed over decades, and it's constantly evolving. But these things in the box here, the Ci and Cm meteorites, are the most primitive materials we have. Their basic chemistry is the same as the sun, okay? They have interacted with water, they have been exposed to a little bit of heat, but other than that, their chemistry is fundamentally the same as the solar nebula when our sun was forming. That's what makes them very interesting to us. So let's talk a little bit more about carbonaceous chondrites, this kind of material that we're talking about. They are carbon-bearing stony meteorites. So if you've seen some of those meteorites that are polished, they're like metal and they have these really cool patterns in them. Those are iron meteorites. This is a stony meteorite. It literally is like any stone you might pick up on the ground. There's no you know, excess abundance of metal in it or anything like that. They're really hard to find in part because of that. You pretty much either have to see them fall and then go get them, or you go pick them up on an ice field, or like, which is Antarctica usually, or you find them out in the Sahara where there's nothing but sand as far as you can see, and then there's a rock sitting there and you're like, well, okay, it kind of had to fall out of the sky. So these meteorites were never melted. That's the undifferentiated part that I was just talking about. They formed in the solar nebula by sedimentary processes. So I think most people know what a sedimentary rock is, but if you don't, I can tell you, you probably know what sediment is. So you take sediment and you find a way to glue it together. So all these little dusts and bits and, you know, pebbles and whatever, you can glue all that together and that makes a sedimentary rock. Well, the same thing happens in the solar nebula. You have particles flying around, gravitational forces pull them together. They might have ice that helps bind them together and they become rocks. The chondrule part here is what makes them really interesting. Chondrules are little solidified droplets of magma, okay? So melted silicate rock. And I'll show you some pictures of those in just a moment. I mentioned they're most primitive. They've got, you know, some of them have had interactions with water or heat. They do have a number of different asteroid parent bodies. So when I talk about a parent body, it means that whatever asteroid I'm talking about, including Bennu, hasn't always been the way it is today. Bennu has a parent body. It has a parent asteroid that it came from. And there's been collisions and things in the solar system that break up asteroids. And so we try to trace these different groups of meteorites back to parent bodies. And then they are comprised of different kinds of minerals. Those minerals can be silicates, which means they are silicon oxygen based. They can be oxides, which is just oxygen based. They can be carbon based, sulfur based, and then we have organic compounds, which are carbon, nitrogen, hydrogen chemistry. That's the stuff that makes us up. They are up to 22% by weight water. There's actual H2O in their structures. And if that seems weird, if you take a step back, we're 85, 90% water. We're not flowing, we're not ice, but we are made of water. So there is H2O in our chemistry, and there's H2O in the chemistry of these rocks. And what makes that really interesting is that it's the impact of meteorites like this and their parent bodies into places like the Earth that we think this is how organic material was delivered to the early Earth. This is how water was probably delivered to the early Earth, is from asteroids and comets. Just as a point of reference, because I like to try to give people something that they can relate to understand what some of these minerals are. Here there's this green crystal called olivine. It's one of these silicate minerals. If you have seen this before, you have seen it as the semi-precious gemstone called peridot, which is probably 1 in every 12 of you is your birthstone. And then this material here called serpentine is another silicate. It's basically olivine, which has no water in it. It's olivine with water in it, but that makes it a different mineral. There's an oxide called magnetite. It's an iron oxide. There's another iron oxide called hematite that you may have seen as jewelry. It's a very common sort of gunmetal, gray, polished, shiny material. It was popular probably 10 or 15 years ago. It's less so now. The other form of iron oxide that you probably are well aware of and deal with is, somebody say it with me, starts with an R. Rust. Yeah, this is just a different chemical arrangement of iron oxide that makes it a different mineral. And then the last one over here is a mineral called pyrite. Most of you probably run across that. It's called fool's gold. It's a sulfide, so it's predominantly sulfur-based. So all of those things are making up rocks that actually look like this, not like these nice pretty mineral specimens. So the question is, why aren't the meteorites good enough? We have these meteorites, we know what they're made out of, we know there's water, we know where they came from, we know when they formed. Why aren't they good enough? Mainly because if we're trying to understand the early organic chemistry of the solar system, the last thing you want is to contaminate your sample. And so when a meteorite goes through our atmosphere, it interacts with our atmosphere, the chemistry in our atmosphere, the water in our atmosphere. Water is a wonderful agent for chemical alteration. It lands on the ground, it interacts with the biosphere that's here. Even if you go out and pick it up 5 minutes later, it is contaminated. And so that is why meteorites aren't that great. Another reason is the context. We don't know where they came from. They literally fell out of the sky. That's about the most we know. With a lot of meteorites, we know that they come from certain asteroids or comets that, you know, produce meteor showers and things like that. But we don't know where on a body they came from. We just don't have any context for them. So that's why we want to go and get the sample from a place that we can characterize very, very well. All right, this is another carbonaceous chondrite. This is a different group. This one's called Allende. You can see the fusion crust is this dark stuff on here. That's where the surface melts as it's coming through the atmosphere. But the inside is well protected. These fusion crusts are usually only 1 millimeter or 2 thick. And by the time this thing lands on the ground, you can pick it up. It's not burning hot or anything. If you cut a slice through this rock, this is what it looks like. You'll see these white things. They're called calcium aluminum rich inclusions. I'm not going to talk at all about those, but the little dark spherules here, those are the chondrules. And these are what they look like under a microscope if you play funny tricks with the light. 500 microns is 0.5 millimeter. And for reference, a human hair is usually anywhere between about 50 and 125 microns. So these are these little spherules that were melted, molten material early on in the solar system history. They basically freeze, and then they get incorporated into this sedimentary rock along with all the other bits and bobs that are floating around out in the solar system. But we don't have anything like that on Earth. All right, so how did we get to, you know, we've got all this background, we know why we want to do all this. How do we figure out where to go to do it? Okay, this is one of my favorite parts of this whole talk because I think this is just such a nice way to think about how you go about flying a spacecraft mission. You have to make so many decisions, but you have some starting point. So in 2009, when we started writing the proposal for this mission, we knew of about 500,000 asteroids. So we had 500,000 asteroids to choose from. Okay, well, so what else are we trying to do? We've got this security aspect. We're worried about, interested in potentially hazardous asteroids. So we said, okay, we're just going to look at the near Earth asteroids. We're going to ignore everything that's out in the main belt, out beyond Mars. So that cuts it down to about 7,000. Okay, that's still a lot to choose your favorite from. So we said, okay, well, what else do we need to worry about? Well, we need an optimal orbit for sample return. Most NASA missions, or missions that anybody flies to a planetary object, you go there and you don't try to come back. You stay there. You stay in orbit, you land on the surface, you never try to come back. We were going to collect a sample that had to get back to Earth. So the spacecraft had to not only go out there and do operations, it had to get back. So you want an asteroid that has an orbit around the sun that makes it easy to do that. So we said, okay, that brings it down to 192. Okay, this is a number you can actually start to begin to wrap your brain around. However, a lot of those asteroids are the size of this room, okay? They're not that big. And so we really wanted something, we were gonna need to operate an entire spacecraft around this object. So we needed something big enough to operate around, to fly a spacecraft around and to sample. And so we said, okay, we need something that's more than 200 meters in diameter. Now that brings us down to 26, all right? We're almost in fingers and toes territory now, and you can actually really start to think about which one is better than the next. And then we said, okay, well, but we have this other high priority objective about origins, organics. So we need one of these carbonaceous asteroids. Doesn't help us to go get a differentiated piece of Mars. We want to know what the early solar system was like, and the carbon-rich materials are where that's at. That got us to 5. And so from there, we had 2 primary choices. One was Bennu, and the other one was an asteroid called Ryugu, which, if you follow this kind of stuff, Ryugu is the target of a sample return mission by the Japanese called Hayabusa 2. So that was our backup asteroid. So we went here and they went there. I will point out that as of 2024, this number of total asteroids is well over 1.3 million now. And 35,000 of those, as opposed to 7,000, are near-Earth asteroids. So we keep discovering more all the time as our telescopes get better and better. So when we decided on Bennu, we used some radar data of the asteroid to generate what we call a shape model, which is exactly what it sounds like. You use radar data to sort of say, okay, here's what we believe the shape of the asteroid to look like. And you can see that we actually got it pretty well, because this was generated before the very first picture of Bennu that I showed you at the beginning of the talk. It's about 510 meters in diameter. That's about 1/3 of a mile. So you could walk around this thing in a reasonable amount of time. Empire State Building and Eiffel Tower for scale, just to give you a sense. This thing is still pretty tiny by solar system standards. It is what is called a B-type asteroid. The B actually means blue. It has a visible blue slope if you look at its spectrum. An entire day on Bennu happens in a little over 4 Earth hours. An entire year on Bennu, however, takes 437 Earth days. So it's got to go, it has to go further to go around the sun. Its mean density is close to that of ice. It's about 1.2 grams per cubic centimeter. The average Earth rock is somewhere between 2.7 and 3 grams per cubic centimeter. Its average reflectance, or how bright it is 4.4%. This is incredibly dark. This is probably darker than a charcoal briquette. It is just dark. There is almost no light bouncing off of it. For reference, the average reflectance of the moon is 12%. So that gives you a little bit of a relative sense. So if we go back to high school science class for a moment, you may remember the electromagnetic spectrum here. So we have our high energy waves and particles here, and we have our low energy ones here. So X-rays, we all know about X-rays for seeing inside the human body. They're high energy, which is what makes them damaging to us over time. They disrupt our cells because they're small and they interact with them. The ultraviolet is just the short side of the part of the spectrum that we can see. This little tiny wedge in here called the visible, that's what our eyes see. Of this entire spectrum, that's the only part that we can actually see. And so our rainbow, our blue to red visible spectrum is in there. Infrared is what we usually think of as heat energy. That you can detect, you go stand next to a radiator and you're feeling infrared energy. A lot of you may have familiarity with infrared cameras. That's a That's been a much more common thing in recent years. Microwaves, obviously, we know about microwaves. They have an energy that's really good at exciting water molecules, as it so happens. And that's how microwaves work. They excite water molecules in your food. And then radio frequencies. This is how we communicate. It's how we run our cell phones. It's, you know, all these things. So we have instruments throughout the electromagnetic spectrum that help us measure as many different things as we possibly can about this asteroid. And so all the ones up here, Rexus, OSIRIS, and Otis, these are all for determining mineral and chemical composition on the surface. OCAMS is a camera suite, so that is literally taking visible pictures that we can then look at. We have what's called OLA, it's a laser altimeter. What it does is it helps us make a topographic map. So the way it works, it's literally kind of like this laser pointer. When I click the button and the red light appears, that's happening at the speed of light, right? We can't, I mean, this distance is so short that it's instantaneous. But when you are away from a planetary surface with your spacecraft and you shine this, you can actually look at the time it takes for the light from when you hit the button to when you see it there, which is how long it takes for the light to get there and travel back to you. From that, you can determine how far away the surface was. It's very, very straightforward kind of stuff. It's like, okay, if it comes back faster, that surface was closer. That's all it is. And then we use our spacecraft telecommunications even for some kinds of science, understanding the gravity of the object and all of that. So here is what Bennu looked like when we arrived in December of 2018. This is a nice little Mercator map of most of the object. These are the 4 images that were the little movie that I showed at the very beginning of the talk. Here's what it was when we got much closer to it and could actually start to resolve things a bit more. This is just a bigger version of the one you saw already. You can see that there are darker rocks and lighter rocks. I'll show you another one in a minute. There's some really big rocks. Here is a nice close-up view of what the surface looks like, though. We saw that and we all just about lost it because our first thought was, how are we going to sample that? How do you get near that? This scale bar down here is 24 feet across. That's how big these rocks are. They're huge. They're enormous. We thought the asteroid had about 2-centimeter rocks as the average rock size. That was because we made assumptions in how we generated that information that turned out to be incorrect. And that was one of the things we learned from this mission, was we learned that some of the things some of the models that we use to predict things like the nature of planetary surfaces were wrong. And so we had to have this realization of, oh, okay, well, now what? So we'll come back to the now what in a little bit. This is one of my favorite images of the mission. It's, you know, a nice kind of limb view of the asteroid. It's like, oh, there's these nice stars back here. Except there's an astronomer on our team who looked at this and said, I don't recognize those stars. I have no idea what that is. What we figured out was that these are actually little particles being ejected from the surface of the asteroid. We still don't entirely understand how that happens, but the predominant theory is that because there is water in the structures of the minerals, and this thing is rotating through the sun's energy every 4 hours, and it's in space, so it's got no atmosphere. So it goes from being exceptionally cold to exceptionally hot over a span of about 2 hours. And we think what this might be is basically freeze-thaw cycling. So the same freeze-thaw that in the wintertime cracks your sidewalk or your pavement or makes your potholes bigger, we think that that kind of thing could be happening here. Most of these particles don't escape the gravity well of the asteroid, they fall back down. So that was one of our really cool results. We also discovered these rocks on the surface that were on a scale that we'd never had hints of from meteorites. So this boulder here is about 21 meters across. It has these sort of light and dark areas on it, and we didn't expect that at all. We call that a breccia. So to a geologist, a breccia is a rock that is made up of big angular fragments of other rocks, and they've gotten glued together. What we also saw up here and zoomed in over here was this kind of thing. We called these campfire rings. And it turns out we think that this is just one of these that's fallen apart. So it's not being held together very tightly, and something allows it to break apart into these different pieces that originally were all held together. We'll come back to why this matters when we get back to the sample. So now in terms of the minerals and the water that they carry, I'm going to show you some squiggly lines, but I'll hold your hand, don't worry. We talk about hydration in asteroids and in minerals. Hydration can mean chemically either water, H2O, or it can mean hydroxyl, which is OH. But we primarily see that in carbonaceous chondrites and minerals that are called phyllosilicates. So I talked about silicates being silicon oxygen rocks. The phyllo is Greek for sheet. So it basically is just telling you that these minerals at the atomic scale are arranged in sheets. Think about phyllo dough, for example, as, sheets. You may more familiarly be familiar with them as clay minerals. Kaopectate is made of a mineral called kaolin because kaolin is really good. Clay minerals are really good at absorbing water. So it does its job that way. In the shorter wavelength part of the spectrum, this is still beyond red, beyond what our eyes can see. We can see the signal of water in what we call the 3 micron band. And it's not actually at 3 microns in these samples, it's more at 2.7, 2.8. But this is a band due to hydroxyl and or water. So we see this on Bennu. So we know that we've gotten that part right. When the actual band position, like you can see here, the dotted line is just a constant reference point. You can see that this meteorite called Avuna, its band minimum is over on this side. And then as you go down the plot, the band minima are actually shifting over to longer wavelengths. That tells us something about the chemistry of those particular minerals. So that's as far as we're going to go with that. However, the spectrum of Bennu goes on into the mid-infrared. And so this is what its spectrum looks like. Here now we're talking about wavelengths closer, 7, 8, 9, 10 microns. This is if you've ever had a FLIR camera or seen somebody use an infrared camera at your house to look for heat leaks or anything like that. Your typical infrared camera is measuring wavelengths around 10 microns. So we can compare that to meteorites as well. And we can, again, you don't have to know what these bumps and wiggles mean, but you can just see that they're different from each other. Bennu looks a lot like the ones up here at the top, more so than it does these guys. And it turns out that these are ones that have interacted the most with water, and these have been heated. And so we can say right off that Bennu is more associated with meteorites that are aqueously altered, have seen interactions with water, and were not very heated. And so based on what we know of the meteorites and what we can detect from these actual spectra, we said, okay, we think the sample is going to be made of more than 80% minerals that have water in them. And that's exactly what we wanted. Okay, so we also found some really bizarre boulders on the surface. These are sort of 2 and 3 meters. That's the scale bars on here. These extremely, extremely bright rocks. They don't look like the rest of Bennu. And we think that what they are is actually pieces of Vesta that have fallen onto this asteroid. So there are meteorites called howardites, eucrites, and diogenites, or we call them the HED meteorites. And they are known to have the same kind of mineral makeup as the asteroid Vesta. So, it's like, oh, well, this seems very strange. Fireworks? But, it's funny, we think of, or I at least think of meteorites as, oh, they're rocks that fall on the Earth. Meteorites happen everywhere in the solar system. There's stuff flying around. It's not just hitting the Earth, it's hitting other asteroids. They're landing on Mars, they're landing on the moon. So we found meteorites on an asteroid, which I think is kind of cool. And so we can use this information to start to think about how they were delivered The people who study this kind of thing are in a totally different field, but they think about what this means for the collisions between asteroids out in space, and how much that continues once the planets start to form and start to sort of suck up most of the loose material that's flying around out there. Okay, evidence of water circulation. We saw these rocks that had these interesting bright lineaments or linear features in them. And we thought, well, that's strange. And we used the spectrometers to understand the composition of the minerals. And we noticed that the abundance of carbonate minerals, so these are carbon-oxygen minerals, were more abundant in the places where we saw these features. And so we think that these are veins. And so to a geologist, a vein is just a fracture in a rock that's had fluid flow into it and through it. That fluid evaporates and it precipitates out minerals, okay? And so the carbonate has precipitated out of a fracture cut into these rocks. So you already know that the carbonate is younger than the rock that it's in. So I just said that part. We have not seen anything like this in meteorites at the kinds of scales we're talking about here. So again, this is a 2.8 meter scale bar. This one's 2 meters, 22 meters. So these are centimeters in scale. We've never seen anything like that in meteorites. So that was a discovery. We have also seen evidence in the spectral data of other carbon-bearing compounds. I'll come back to organics. That's really what we're talking about here when we get to the sample. So the next question is, well, okay, so you've got this big asteroid. I told you that when we got there, we all really had an oh my gosh moment, because we're like, how are we going to sample this thing? It doesn't look at all like what we thought it was going to look like. We had an original target ellipse, an area that we were thinking, okay, we can drive the spacecraft to an area about 50 meters in diameter with pretty high confidence. We never found a place that was that big on the asteroid to take the spacecraft. So I give all the credit in the world to the folks who are the navigators, the spacecraft folks, most of whom are at Goddard Space Flight Center in Maryland. They figured out how to reduce that diameter to 10 meters. So this is about 35, 40 feet. We had no choice. That was what we had to do, and they made it happen. We narrowed it down to 4 places on the asteroid where we thought we could fit this 10-meter spot. The one up here, Nightingale, is the one we ended up choosing. This one's a crater. It's a little faint, but you can probably see that this is a depression. This one's also a crater. This one is maybe not a crater, and this one is probably also a crater. But we ended up choosing this site, and that was where we went going forward. I'll observe, though, that this is a 10-meter scale bar. That rock is 10 or 20 meters high and at least 10 meters across. We called it Mount Doom. All right, so how do we actually go about collecting the sample? I told you we don't land. I already oriented you for the spacecraft a little bit. We have this arm. There's a spring in this dark area here. So when you contact the asteroid, there's a little bit of a spring, like a shock absorber, basically, that gives a little bit. But the business end here is the touch and go sample acquisition mechanism, which in meetings gets really long to say, so we call it TAG-SAM. It's this little ring here, and it touches the surface, and on the flat surface out here are those contact pads that collect from the uppermost surface, and then we disturb the surface to generate with compressed nitrogen gas so that it disrupts the surface and kind of pushes the sample material into this ring, okay? So what I'm going to show you now is a profile view of how this works. So you contact, the gas is spread out, it causes the rocks to get disrupted, and they go up into the walls of the chamber here, and that's how we collect the sample. These little things these are flaps. They're made out of mylar, and so when the gas is ejected, the mylar flaps are lifted as the sample material goes in there. Yeah.
If you were sampling from craters, how could you distinguish original material from what made the crater?
From the impactor? That's a great question. Usually the impactor is destroyed, and for some of these small craters, the crater size is much larger than the actual impactor. So, but there's potential for some of the impactor to actually be in the sample. It's not impossible. Okay, here's what it looks like in real time. These are just still images stitched together into a movie. That's how long it takes. That's it. And you can see by the way the rocks fragment and just everywhere, they're really, I mean, almost fluffy as rocks go. They really break apart. So that's literally as fast as this occurred. And then we back the spacecraft away and we're done. We had extra gas canisters in case this didn't work the first time. We didn't need to use them. And so the way we knew this, that we didn't need to use them, is because what we do is after we've backed away and we're at a safe distance, you take that tag SAM, it's pointed this way to do the sampling, you go whoop, and you take a picture. And that's what this picture is. So that is the business side of the sampling head. These large discs here are basically stainless steel Velcro, and those are the uppermost surface contact pads. Inside here is where the mylar flap is, and the samples go in there. This little distortion you see here on the left is actually a distortion in the mylar flap. The mylar flap got trapped open. This is bad. And I'll show you why in a second when I click again, but you're gonna see what I want you to do. There's a particle right up here. I want you to watch that particle. That's good. So that's just 3 frames that are repeating. Where's that particle going? Away. This was a very disturbing thing. And not only because we were losing sample mass, you know, it completely changed our operations. We had planned to do various measurements, spin the spacecraft to get the mass of the sample and blah, blah, blah. We saw this and we were like, oh my gosh, the sample is literally leaking out. We have to put this thing away right now. And it was really funny. If you've got an advanced degree, you might appreciate this even more. But, you know, one of the scientists was, you know, looking at this particle and he goes, oh, there goes somebody's PhD thesis. Okay, so we stow it. And this over on the left here, this white thing here is actually the top of the sample return capsule. You can think of that, that's the heat shield basically. And this is what it looks like from, you know, inside view. And this is the lid popped open. This thing folds back and pops it in. And then it cuts a braided cable here. The arm folds back out, the lid comes down, it locks, and now you're done. Except you got to fly back. So now, this is, I'm going to condense a whole lot of time into one slide. We left Bennu in 2021. In September of 2023, the capsule landed in the Utah Test and Training Range. And it was immediately taken to Johnson Space Center in Houston, which is where all the Apollo samples are, where our Antarctic meteorite collections are, any kind of planetary materials that NASA has collected are archived at Johnson Space Center, and they have a curation facility that keeps them all pristine and everything. So basically the way this works is the sample return capsule is released from the deck of the spacecraft. The spacecraft does a maneuver to point itself away from the Earth. The capsule then continues on towards the Earth. It will come through the atmosphere, burn off the heat shield, it pops a parachute, and then it lands in the desert. And this is the actual sample return capsule sitting in the desert the day it landed. Beautiful, perfect. And now here is the tag SAM back on Earth in the lab. This is at Johnson Space Center. So again, you can see the contact pads, those discs here, they're about almost 2 centimeters across. This is, you know, these are Phillips head screws. You can see different kinds of particles. There's sand grains, there's little small rocks. There's a rock here that's actually wedged in by the mylar flap, which is kind of sitting here. The real good, great news that we had was that we got 121 grams of sample, almost 122. We had a requirement for 60. So we doubled the requirement, and we're really frustrated because we think we had 300. But we got 121, so nobody's complaining. Except maybe the principal investigator of the mission. He wasn't happy about that. Okay, so I've walked you through the asteroid, the context, all of that. So what are the observations of Bennu that we've made that now we can use to sort of make some predictions about what we expect to see in the sample? So we know, based on what we saw on the asteroid and what we know about the sample system, that we were expecting anything from submicron to 3 centimeter particles, and the largest particle we got back was 3.5 centimeters. We expected these water-bearing minerals, these vein-filling materials, these iron oxides, and we expected organic compounds. We saw 2 different kinds of rocks in different textures, smooth and rough, more angular and more lumpy. We expected them to have low density and porosity. We thought maybe we'd see some of those meteorite bits in the sample, who knows? We certainly expected that there would be some things that we didn't know about from meteorites that would pop up out of this sample. We thought because of those veins that maybe we would have these chunky carbonate minerals, and maybe even some of those ejected things that went up and then came back down again. Maybe we'll find those in the sample. So from this, we actually do what you hear about in science class. We developed hypotheses to test. Science doesn't always work that way, and that's okay, but actually some of the time it does. And this was what we did. We came up with this list of different hypotheses based on all the observations we made. I'm going to talk about these 3. Every single one of these has sub-bullets and sub-sub-bullets that we can test with this sample. So we'll start off with the idea that, okay, we think that our remote sensing, our spacecraft that characterized the asteroid, did a good job. That's what we think. It did a good job telling us what the mineral, chemical, and physical properties of the sample would be. We said we think there's at least 2 types of rocks based on their brightness and textures. They may or may not have the same composition. Here are 3 pictures of materials from Bennu. And if you don't look at the scale bar, I challenge you to tell me which one's the sample and which one is the asteroid. It turns out the sample is the one that says sample. These are bits that, these are 5 millimeter scale bars. So these are little pieces like this that have these angular and kind of smooth textures. Here's an example on Bennu that's 3.5 feet across. Looks almost the same, almost fractal in nature. Here's the rougher type. We called these hummocky. They are not so angular. They're blobby. They look kind of like the heads of, cauliflower or broccoli or something. And then here's the example on Bennu. Again, very, very similar to what we see in the sample. So we've seen that. This was another one we weren't entirely expecting. These are called mottled, M-O-T-T-L-E-D, mottled lithologies. And they have these bright, relatively bright materials on their surfaces. And we think maybe this is somehow related to these things where we saw the veins and other interesting stuff. So we think from that perspective, yeah, we actually did a really good job predicting some of these characteristics. We said, okay, we think the rocks are going to be dominated by these water-bearing minerals. And we got the sample back and we measured the sample, and it looks a lot like Bennu, which is really hard to see in blue here. Sorry about that. But we can also compare it to these really primitive meteorites that all have a lot of water in them, and they look very much alike. When we do quantitative measurements, yes, in fact, more than 80% or about 80% of the rock is these sheet silicates that have a lot of water in them. So we got exactly what we were hoping to get, and we characterized it pretty accurately at the asteroid. We found organic materials. Now we're changing scales here significantly to much, much tinier things. The scale bar over here is 10 microns, so maybe 1/5 of the width of a human hair. Here we're talking about 2.5 microns, and here we're talking about 0.5 micron. So this is ridiculously tiny. But these are all sample areas where we're seeing organic material in the sample. They are much more rich in things like carbon and nitrogen and ammonia than we have ever seen in meteorites, and even than was seen in the sample returned from Ryugu by the Japanese. It's significant because, in particular, ammonia has an extremely low freezing point. The only way to get ammonia locked into these minerals and organics is to have it happen at a place where the ammonia isn't liquid or gaseous. That only happens in the far reaches of the solar system. So if you're in the early solar system, the sun is nice and hot and big, and it's keeping everything nice and toasty warm in the inner solar system. But as you get to the outer solar system, out where Jupiter is and beyond, now it's really, really cold, and ammonia becomes stable as a solid phase. And so that tells us something about where these rocks formed in the solar system. That's our context. In terms of the organic materials, there are dozens, if not hundreds, of different chemical compounds that the organic chemists on the team found. I don't know anything about organic chemistry other than I am made of it. That's as much as I can tell you. I know that, however, we found all of the nucleobases that are found in DNA and RNA. So there's a link there between the prebiotic chemistry that we see in the asteroids and all of us sitting here today. All right, I want to talk about this because it's interesting. I'm going to introduce 2 words here from chemistry class. Chirality. Before I explain what we found, chirality is molecules have a handedness, okay? We have left-handed and right-handed, right? Handedness is when you have a mirror image molecule. So this is one molecule, this is the other. They're mirror images of each other, but you cannot superpose them and get the same thing, okay? So they have, you know, they look a lot alike, but they're not the same, okay? That's chirality. So all of the amino acids that are chiral amino acids were racemic. So racemic is the other word. Racemic means in all the molecules in your bowl, you have basically an equal number of left-handed and right-handed. Okay, so that's what we found in the sample. Most of the molecules, almost all the molecules, were equal in proportions of left-handed and right-handed. What's bizarre about that is that life on Earth is all left-handed. And we thought, well, we've been thinking this is the origin of the biotic chemistry that makes life on Earth. Why is it all left-handed here and not in the early materials? We don't know. This was absolutely something the organic chemists did not foresee, did not expect. And so it's a really neat puzzle that we're going to have to think about. If this is the stuff, you know, asteroids and comets are delivering organics and water to the early Earth, how did life go down this like extreme path? So very interesting result, even for me, a non-organic chemist. We thought, you know, okay, from what we've seen, there's been geological activity in Bennu's parent body. That's the flow of water, formation of these kinds of rocks that have been all glued together. There are these breccias. And in fact, that's the disaggregated one that I showed you. And now here's a bit of the sample. And I believe these are all about 0.5 millimeter. So the scale is changing, but they're about 0.5 millimeter for each of these bars. And circled here are what we call clasts, or these angular fragments. And so we see that breccia texture even in these very tiny bits of sample material. This is really cool. Has anybody ever had a CT scan? Okay, this is a CT scan of a rock. And so we're using X-rays to look at the inside of the rock and map its shape, and you will start to see the slices get taken away here in just a moment. There we go. And so now you're seeing into the rock, and as those colors change, what you're seeing are different properties of the rock. They're reacting to the X-rays in different ways. So this is a way that we can actually look inside the stones without breaking them apart. And we see all these various things going on. So all of these pieces that got glued together. Many unexpected things, as we predicted. We found minerals of certain kinds that are very, very rare in meteorites or not known in meteorites. In particular, sodium, magnesium bearing phosphate minerals are not known in these meteorites, and we discovered them in the Bennu sample. Phosphates are used for all kinds of things on Earth. As far as minerals go, turquoise is actually a phosphate mineral, but phosphates are used as fire retardants. They're used in food preparation. There's all kinds of things. But a lot of these things are what we call salts. And a salt is simply a chemical reaction. So table salt is a salt. It's sodium chloride, but it is not a phosphate. Phosphates are salts. Table salt is a salt, but table salt is not a phosphate. They're produced, again, by evaporating water that precipitates out the solid stuff that gets left behind. They probably formed on Bennu's parent body. Bennu is not a first-generation object. It is the product of collisions. It is only as a body about 1 billion years old, maybe 2. But it had a parent asteroid. And so that parent asteroid had to be big enough for that water process to flow and flow over considerable distances of centimeters to meters. And so this all has implications for prebiotic chemistry, the potential for astrobiology, what we now think of as astrobiology, which is the potential for life anywhere in the solar system, or even potentially the galaxy, as we see more and more exoplanets being discovered that look Earth-like. So how does the sample compare to the predictions we made? This is the closing. This is it. This is the end. So in fact, we saw the size range we fully expected to see. That was a prediction that came true. That one was probably pretty easy, one of our easiest ones. We had all kinds of predictions about the minerals and the chemicals that we would find, and in fact, we found all of those things. So we did a good job there. We had these expected rock types, which to a geologist is called lithologies. Litho means rock in Greek, so lithologies, different kinds of rocks. The 2 textures, the density, the porosity, the fact that we might see things like those meteorites from Vesta, those we haven't identified yet, but we have seen the evidence of the textures. We've made density and porosity measurements, and in fact it is low. We've certainly seen properties distinct from known meteorites. We haven't yet seen those centimeter scale carbonates. Those have not turned up in the sample, and we don't know if that's because they're readily damaged or there just weren't any where we saw them, or maybe those bright lines that we saw aren't carbonates at all. Maybe there's something else. And then we also haven't found, but can't exclude, that there are some of those centimeter scale particles that were ejected off the surface might be in the sample. I think for me, one of the hardest things to figure out is how would you recognize those? Because they're going to be the same material that's everywhere else on Bennu. So how do you know if that one flew up into the sky and came back down again? I don't know. There's somebody out there who will figure how you know that, not me. So we have done, I think, really, really well. And where we haven't succeeded yet is not necessarily because we didn't do something right, but sometimes because the sample tells you something you just didn't know, you didn't expect. You can't always detect everything from an orbital position. It's like you trying to look across your yard and see what kind of nail is lying over there 50 feet away. You know, there are just things you can't resolve at certain distances. So I think there's going to be a lot more to come from this mission. We are really just starting our analysis, even though it's been 1.5 years and we're coming up on 2 years. The samples are being archived. They're being distributed to scientists around the world to research, and there's going to continue to be more and more discoveries from this. And sample return is such an incredibly valuable tool that we have to understand the solar system. My personal hope, I started out studying Mars. We have plans for a Mars sample return mission. The future of that mission is in doubt right now, but I think we would learn so much from it just on the basis of what we've learned from missions like this alone. So thank you very much for coming. Thank you for listening, and I'll answer any questions you have.
Going back to the slide with the Pigpen Trail
Mm-hmm.
from Peanuts cartoons, is that also potentially a combination of angular momentum and low gravity, along with the
Alone, I don't think so. But what it could be, one of the other ideas is that you've got micrometeorite impacts that could then be ejecting them. But the spin rate and all of that of the asteroid is not enough to just, spontaneously cause the particles to lift. Anything else? Yeah.
That you guys recovered was the supplementary capsule.
Mm-hmm.
Where is the rest of
Very good question. So I mentioned that when the spacecraft drops off the capsule, it diverts because it's on a collision trajectory with the Earth, and so it lets the capsule go. We did a maneuver to take the spacecraft away from the Earth. We proposed to NASA to fly to a new asteroid and measure it. The mission is called OSIRIS-APEX now. It's Apophis Explorer, so it's the OSIRIS Apophis Explorer. Apophis is the asteroid that we're headed towards. Apophis is another potentially hazardous asteroid. It's going to have a very close pass by the Earth in 2029. And so in April 2029, we're going to fly the spacecraft past Apophis right after it comes past the Earth and make measurements of it there. It's a completely different kind of asteroid, so it'll be a completely different science. Whether that mission will happen or not is unclear. Right now, it's slated for cancellation. But fingers crossed. Yeah.
You talk about picking this asteroid a little bit, it makes the planetary formation, but it's still undergoing some amount of aging, right? Which the star or the pre-star cycles that are going in, as well as the solar winds. Can you make some predictions about what it would have been like back then versus where it is now?
Yeah, so the easiest way to do it is, I mentioned those contact pads were there to sample the very, very uppermost surface. They pick up little tiny grains. Basically with the larger stones, those ones that are sort of centimeter sized, basically once you cut into them, what you're seeing is pretty much the original stuff. Once you get away from that uppermost surface layer, you can really see what was there to begin with. So we get to see both. That's the beauty of both worlds. When you're at the spacecraft, when you're on the spacecraft and you're looking at the surface, all of that surface is space weathered to some degree or another, and we have all kinds of ideas about which surfaces are more or less space weathered based on what color they are and what their spectral signatures look like, etc. But they've all been exposed to space by definition. So the sample, just the interior, lets us get at that real, true history. Yeah. Anything else?
So it's clearing up to some degree out there, fading with the visible overhead at least a couple minutes ago. We've got some people that are already ran up to the telescope to get it going. We'll try to see what we can and what's available. Not much available from a planetary standpoint. Saturn's not up until much later. The moon, again, not until probably